Thank you, Richard. Good morning, everyone. It is really a great pleasure to be here today to tell you about multi-robot systems. And I want to start by thanking you for being here so early, especially after that wonderful night at the museum and all the drinking that followed. Now, if you have worked with multi-robot systems, you know that communication is powerful. It can assist perception, it can assist control, it can enable a whole set of new capabilities for robots. But communication is also a big challenge, and I think we've all seen it even with the Wi-Fi system in the room this time. But today, I'm here to tell you that communication can be your friend, not your foe, and I'm here to tell you how. So let me start by reviewing that multi-robot systems operate in complex environments, which they sense, and then they move to support the task they have to do. And the robots are connected by communication. And the opportunities in the space are really at the intersection between control, communication, and perception. And these opportunities lead to a whole new set of problems that are difficult to solve with single robots. Now, there are so many types of multi-robot systems in our world today, and we will see plenty of them in this session. There are systems on the ground, there are systems in air, there are systems in water, there are systems connected by Wi-Fi, by RFID, by physical connections. And I won't go into too many details because I know you will see a lot of interesting systems today. And there are also many, many different areas of application. And for all these systems, there are two fundamental challenges. Now, the robots in these systems generally communicate and sense only locally, and from this local information, the system tries to deliver global behavior with performance guarantees. Now, this is usually a big challenge, especially the guarantees part. Going from local information to global behavior, furthermore, requires communication. And in our community, this is treated as a black box. Now, to deal with communication, we currently use two methods. We either assume the disk model. That means that you draw a disk around your robot, and any robot that is geometrically located within that disk is assumed to receive all the messages that our robots send. And so this is a nice, simple geometric model, but it is oblivious to the channel, to the communication channel. On the other hand, we have sampling methods, where the idea is that the robot moves along some direction in space, and it samples the communication quality, and that aggregates some kind of a model, some kind of one-dimensional model, because the robot only gets the amplitude of the signal, does not get anything about the phase, and in other words, this is also a very simple model. So in general, the problem with both of these approaches is that they attempt to model and predict communication. And modeling and predicting communication is notoriously hard. Actually, it is impossible. And any robot control method that relies on such methods is fraught with noise. So let me give you a more concrete example. So this chart shows what happens in reality in an open space. So we have a piece of the data center at MIT, and we have a robot that sweeps up and down, measuring the signal strength. In green, you see the spots where the signal is really good, and I guess there is a you see the client, and there is an access point that is line of sight, sort of in the lower corner there. So you see in green all the spots where the communication is really good. You see in yellow the spots where the communication is so-so, and in red you see spots that receive no communication. So look at those lines. Those green lines where you have perfect line of sight and you expect to have communication everywhere, they're full of red dots. So if your robot happens to be there, it's going to be stuck. So the bottom line is that trying to model and predict communication is really complicated. And there's a whole community out there who has been thinking about this problem for many, many years, and we still don't have good models. And the other problem is that expecting that the Euclidean disk model will actually get your robot system to perform correctly is plain wrong. It does not work. Okay, so at this point you might think, well, clearly communication is a foe. But in fact, we can improve a lot. And the main idea is to try to treat communication like we treat any other signal we perceive in robotics. So think of communication as perception. Instead of predicting, can we find a way to measure the signal directly, but in a way that actually makes sense? And so so our idea was to figure out a way to enable a robot to estimate communication instantaneously at the point of action along every single direction in space. Then the robot can use communication gradients to follow where the signal strength is good. So how can we do that? Well, here is an idea that came out of the networking community. And this idea is that there is multipath, and multipath can be exploited. So the insight is to take advantage of how signals propagate in the environment and to actually try to measure the angles of arrival for these signals. And then what we can do is we can plot a graph or a communication profile at every point where our robot exists. Okay, so the communication profile gives us peaks where there is good signal quality and gives us flat lines where there isn't. And furthermore, we actually get an added bonus because nodes that are nearby have similar profiles with small shifts at the peaks. So if we could measure and create these profiles, we could also know who's around and who's close to whom. All right, so what is the trick for doing this? It turns out that we can apply some standard tricks developed by the networking community, and we can actually measure the channel. We can actually measure these profiles using a method that is inspired by SAR, by synthetic aperture radar. So we can't put radars on small robots, but we can take advantage of the movement of the robot in order to effectively emulate the behavior of a SAR system. And that's all there is to it. So this is a very simple trick that works extremely well. So here is in more detail what we can do. So say you have two robots that want to communicate. If they're practically in a line of sight communication, you can look and see that where the robots are directly pointed to each other, the signal is super good, and where the robots are away from each other, then the signal is less good. And if you have an obstacle in between the two robots, we can take advantage of that obstacle, and we can measure the multipath angles, and then we have multiple peaks where the signal is good. So I'm very excited about this, because this is a way of thinking about communication in a uniform way, in the same sort of way that we treat perception, and we can couple it quite directly to action, to control. So to give you an idea for how this might work, I want to show you a very quick solution that uses this idea to solve the mobile base station problem. So the mobile base station problem is the following. You have some nodes that move in the world. They can move in the plane. They can move in 3D. You don't know how they move, but you want to you want to make sure that they are constantly within good communication coverage from each other. So you'd like to put some robots in the system that act essentially as robot base stations, that observe how the clients move and position themselves to ensure that the system is connected. Well, it turns out that we can use the measurement I have explained today to model this communication coverage problem, to model how to place the base stations as an optimization problem. And as an optimization problem, that's actually fairly general and fairly effective. You can decide that you want nodes in one part of the system to have higher communication bandwidth. You can decide that in another part of the system you don't want the same communication bandwidth, and that you can decide that this communication bandwidth, in fact, this desired communication bandwidth varies over time. So, for instance, later on, you might want a different configuration where different nodes need to have most access to the channel. So this is really cool because you can think about this as a building block for making multi-robot systems where communication helps them, where you can count on the quality of communication. And if communication is not good, you can detect it, and the robots can do something to reposition themselves to make that communication better. It's a way of combining the geometry of moving in space with a signal processing that gives us information about communication. And in fact, the way we can model this problem is actually as a fairly standard optimization problem that captures channel feedback as part of the cost function. So we won't go into the math, but I can tell you that in fact we end up with adaptive algorithms that are very stable, that require no models and no map for communication. And to convince you that this is the case, I want to show you an example where we are running this algorithm with two robot base stations. They are robot R1 and R2, and in this picture you see clients 1, 2, and 3. They are stationary at this point, but they can also move. And the first phase of the algorithm, you see the base station sort of moving around, trying to do measurements and communication profiles, and then following the gradients of those communication profiles to ensure that the robots they have to provide communication to are actually connected. And at one point, the environment changes. In fact, Stephanie comes in and changes where the obstacle is located. Now all the communication profiles change, and the robots reposition themselves. The base stations, in fact, swap roles because the occlusion makes it better for robots to provide communication in other ways. You can see at the top the cost function that is driving this optimization. So think of this as a building block or as a brick for creating multi-robot systems that will not fail because communication is flaky. And so what else can we do with this? Well, we can take these systems and we can adapt them to very large-scale systems. So in this case, we're actually doing a simulation where on the left you see dots that correspond to locations of about 500 taxi cabs in San Francisco. And the taxi cabs are moving according to what their clients want, so very unpredictably. So in this setup, we have 3 flying robots, quadrotor robots, which are tasked to provide continuous communication to all the taxi cabs on the ground. And we have a simulated model for how the measurements, the communication measurements work in the system. You can see the robots moving in the world, and you can see them. You can see one robot going all the way out to provide coverage to the taxis that are way out of the city, and you see other robots clustering in the center of town where you have more robots. So what's really interesting in this movie is you can see scalability. So you can see that these methods are applicable to to large groups of robots. You could also see the adaptation. You could see how these robots can actually keep track of nodes that move unpredictably. So here's another thing you can do. So I'm really excited about Google's Project Loon. So this idea is to create a wireless infrastructure for remote areas to provide connectivity to places that are currently not connected. And there are so many different applications. There are many rural areas where this could be the only hope at the moment. So what they have is these balloons that just kind of float in the atmosphere, and they have base stations attached to them. But the problem with these balloons is that they go with the currents, so you cannot really direct them. Well, the algorithms that I have just described are eminently applicable to make the Google Loon project provide communication connectivity in a purposeful way. So if you have a particular area of the world where people are not connected, people do not have internet access, where internet access is too expensive to install, you can imagine taking Project Loon and algorithms developed by our community and solving this big, important societal problem. So I think this is really cool. So the clients end up being houses and people on the ground, and all you have to do is make these balloons controllable and movable. So perhaps some of the students in the audience will get inspired and create such a balloon for these future applications. All right, let me tell you what else we can do with these systems. So we can take these systems and apply them in really complex environments, environments you might expect in fully automated factories, where you have many robots that have to talk with each other in order to ensure that robot tasks get completed. And this is just a short sequence from a project we are doing in collaboration with Boeing, where the idea is to get a team of robots to talk to each other and work out a plan to fully assemble a plane wing, or as you see in this picture, a miniaturized model of a plane wing. So here we have a system of 4 robots, each with different capabilities, but they have to talk a lot. And you can see in this sketch on the side, you can see circles that tell you all the points where the robots have to negotiate information in order to solve a task. So for instance here, 2 robots have to pick up a part and coordinate when to grasp it, when to start moving. The part gets transported to the assembly location, and once it gets there, there are other robots that have to come in the loop, because the robot that's waiting there is waiting to put it's waiting to connect the skin with the ladder of the wing with a fastener. So here's this robot who is continuously talking with the other 2 robots to decide, well, when is the part down? When can I start looking for holes? Are the holes aligned? Well, if the holes are not aligned, you guys have to shift, turn left, turn right. So you can see that there are so many instances here where having reliable communication is really important. And being able to adapt in case communication all of a sudden goes away is critical to finishing and delivering on this task. So at this point, these robots can put fasteners in all day long, and you have seen the first one. So I want to tell you just a couple of other, I want to give you one more challenge about multi-robot systems and how you interact with them, and that is tasking them. So in many cases, the task is already given to the robot as a pre-programmed task. But we would like to add the human in the loop. So we would like to make the communication problem even more complicated by allowing humans to adjust the task and to change the task. So here what you see is an example where we're trying to provide, with a single input, we're trying to tell this team of robots to navigate in a particular way. And we'd like for these robots to get the high-level description of the task, in other words, move from here to there. And then we'd like for the robots to work it out among each other, how to make that, how to travel along that trajectory. So how to keep at sufficient distance away from each other so that you do not collide with each other or interfere with each other, but at the same time you deliver on the task and you keep the robots connected. And this is really a huge problem for multi-robot systems. So thinking about how to program them, how to allow a human to adjust the task and to change the task in time. Now, I see that I'm nearly out of time, and I just wanted to give you a final look at a video that shows you that we can actually learn a lot from humans when we think about communication. So here is a fun video I hope you will enjoy as the last piece of the talk. So this was an exercise to controlling humans, to giving single input controls to humans carrying umbrellas. And we recorded what happened. Then we tried to analyze, by looking at the pixels formed by the umbrella, we tried to analyze what the humans did in response to instructions. So let me conclude by saying that I hope I have convinced you that communication can be your friend, that the DISC model does not capture realistic communications, that communication as measurement is practical. And finally, I would like to thank Kevin and team for giving us a Ferris Bueller's moment last night. Thank you.
Hi, my name is Ellison. I'm presenting the work Autonomous Wireless Backbone Deployment with Bounded Number of Networked Robots. I'm from Universidade Federal de Minas Gerais, Brazil. In 2005, Hurricane Katrina hit the east coast of the United States, destroying the main communication infrastructures. Letting the first rescue teams unable to communicate properly. Here I'm talking about the firefighters, policemen. In such scenarios, we could use networked robots to create a network supporting these rescue teams until the infrastructure is restored. The problem can be defined as given an environment map, a set of clients, and a set of networked robots. The goal is to create a network interconnecting the clients using the networked robots as routers. Here, our approach has two phases. First, we create a Steiner tree interconnecting the set of clients. A Steiner tree is defined as the minimal tree interconnecting a set of points. Here we use an obstacle avoidance Steiner tree, so we are able to deal with obstacles. Then, in a second phase, we use a state machine to autonomously guide the networked robots to create a network. Our methodology is autonomous. Each robot is able to run a state machine, decentralized, and it shows that it needs a bounded number of networked robots. Here we have a simulation, a video of a simulation. The black dots are the clients. First, we create a Steiner tree that is represented by the black line. The robots are represented by the squares. The color of the square is representing the state of the state machine. I will show more during the interactive session. Thank you very much for your attention.
Hi, my name is William Bexley. I'm a PhD student at the University of Minnesota. This work involves the notion of point cloud culling. By culling, we mean given a set of point clouds, we're interested in transmitting a subset of those point clouds over the network. There's two motivating factors for this research. The first motivating factor is the availability of low-cost RGBD sensors. These sensors have enabled the robotics community to create rich 3D data sets. The second motivating factor is cloud robotics. So small robots often have limited onboard resources. If we have a remote computing infrastructure, we're interested in offloading those data and computations. Now, in practice, if we equip a robot with an RGBD sensor and connect to the network, we experience problems with potential bottlenecks when transmitting the data. With that, we come to the statement of the problem, which is the following. Given a robot vision task, such as object classification, can we intelligently throttle RGBD data between a client, which is our robot, and a server, which is the cloud? And the answer to that question is yes, we can. The client can make use of redundant information in point cloud frames to reduce data transmission, and we can allow the server to analyze the received data and make adjustments to the client's rate of transmission. On the client side, we define a scene entropy using the voxel density of the point cloud provided by the robot's current point of view as a probability distribution. Movement of the robot and/or objects in the scene results in a change in entropy. We're interested in transmitting sequential frames with a significant difference in entropy. On the server side, we can allow the server to adjust the entropy threshold to allow the client to transmit more or less frames. When the system is performing optimally, we can decrease the sending rate of the client by increasing the entropy threshold, thus reducing traffic on the network. So to prove the point cloud culling method, we did the following experiment in object classification. We have a robot trained on 3 sets of objects, then we determine how many data frames are transmitted by the robot using the point cloud culling method versus not using the method. In summary, clients ideally make use of processing and data resources when connected to a server in a cloud environment. We can also have the role of we can have the server be used to provide guidance to the actions of the robot. If you're interested in more details on the algorithms and experimental results, please talk to me during the interactive session. Thank you.
Good afternoon. My name is James Steffen. I'm from the University of Pennsylvania, and I'm here to talk to you today about robust routing and MCTP for connectivity management of mobile robotic teams. This work is done in collaboration with Dr. Vijay Kumar, Dr. Alejandro Ribeiro, Benjamin Charo, all from the University of Pennsylvania, as well as Dr. John Fink from the Army Research Lab. The problem that we are focused on is, given a team of N robots and a task objective, how can you have the team of robots self-deploy into a network such that the task is completed, as well as communication being preserved back to the access point for all the robots? The thing that we do first is we model the end-to-end data rates. So first we start with the point-to-point data rates, which is a function of the inter-robot distance. From that, we can determine a mean and variance for the channel using a Gaussian model. Then the next step is to determine routing variables for each robot in terms of what robot I sends to robot J. From this, we can determine the instantaneous data rate that a robot can inject into the network while preserving queue stability, as well as the average and variance of such values. Using those values, we can then make an optimization problem such that we, again, seek to minimize the global potential, as well as ensure the network. Since the input rate of the data is now a random variable, what we can do is we can probabilistically guarantee that the network is maintained such that each robot is able to inject a certain amount of data into the network above some epsilon percentage. This problem can then be solved easily and efficiently as SOCP. For the motion planning portion, we use rapidly exploring random tree, where a point in the state space is feasible if there is a feasible solution to the SOCP for the network survivability. Then the extends method takes care of the robot dynamics to make sure that it is a safe trajectory. In the end, we end up with a trajectory that is both physically safe and we have a high probability of network survivability for the duration of the experiment. Because these are wireless networks that are inherently unstable, TCP has some issues where you end up with inefficient use of the channel. UDP, on the other hand, has great use of the channel but has no reliability. So what we've proposed is a hybrid solution called MCTP, which uses the benefits of a UDP channel utilization and the TCP reliability. This also is used because it greatly leverages the fixed packet structure that our transceivers use. We ran a series of experiments where we had, on the top, you can see that the blue line is the robust routing, and the green line is a greedy solution that just uses the best path, not taking in the variance into account. What you can see is that the green line varies greatly, while the blue line gracefully degrades as the distance goes out for the robot team in the multi-hop network. And then on the bottom, you can see, using our confirmation protocol in the lower right, you see that the data rates that are maintained, it is almost a perfect channel as the robot moves through the environment, and I'd love to talk to you more at the information session. Thank you.
Hi, my name is Solmaz Kia, and I'm presenting a decentralized algorithm for cooperative localization of group of mobile agents. So cooperative localization is a technique that uses relative measurement among a group of mobile agents as a feedback signal to jointly estimate the location of team members, therefore resulting in an increased accuracy for the entire team. Any effective and correct cooperative localization algorithm needs to keep an accurate track of the correlations that are being created between the state estimate of the team members, both for filter consistency and also expanding the benefit of the update beyond the robots involved in the measurement. But the challenge here is how to keep track of these fully coupled equations without requiring all-to-all communication. The algorithm that we propose is a decentralized implementation of a centralized Kalman filter for cooperative localizations, and these couplings are modeled in the form of cross-covariance terms in this filter. And innovation in our work is that we keep track of these cross-covariances in an implicit manner, therefore we don't require all-to-all communication at all. So to develop our algorithm, we look at the equations of the centralized Kalman filter for cooperative localization, and we identify a pattern that allows us to decompose the coupling terms in a manner that results in a decentralized operation. So in particular, when we look at the propagation equations, we observe that the source of coupling in this stage are the cross-covariance terms. In the update stage, we observe that the part of the Kalman filter that each agent is using to update its estimates depends only on the cross-covariance of that agent with the robots involved in the relative measurement, and also the rest of the terms in the gain belong to the robots involved in the relative measurement. Based on this observation, the strategy we propose to decentralize this algorithm is to eliminate the direct calculation of cross-covariance terms by decomposing it into parts that each robot propagates part of it. And this decomposition is done in a manner that in the update stage, each robot using these new intermediate variables and the information that it receives from the robot making the relative measurement can construct its Kalman filter gain. And this is how our algorithm operates. The propagation stage is fully decoupled. In the update stage, the robot that is making the measurement is the interim master. It requires some information from the landmark robot. It makes some intermediate variable calculations and broadcasts a message to the entire team. And then every robot using this message and its local variables can calculate its centralized equivalent Kalman filter gain. So thank you, and I'm looking forward to discussing our algorithm in the interactive session.
Hi, my name is Jim Price. I'm going to present work that's been done in collaboration between the Worcester Polytechnic Institute and Drexel University for the DARPA Robotics Challenge. So the DARPA Robotics Challenge is a large-scale effort to leverage the state-of-the-art in disaster recovery robotics. It's revolving around 8 tasks where participants were invited to perform that involve complex manipulation. So here you can see 4 of those tasks where our robot DRC U-boat built by our team is performing debris clearing, hose insertion, ladder climbing, and valve turning task, which was the task for which we built this framework. So our approach is a user-guided approach where a set of onboard modules are communicating remotely with the workstation. So the graphical user interface provides task-level command to the user and provides a way for the user to localize objects in point cloud data.
Yeah, he would be giving a talk.
Then we have a motion planning component which generates statistically stable trajectories that respect end effector pose constraints. We have an unreliable communication toolkit that handles network dropouts and delays. And finally, a multi-operator protocol that dictates the behavior that the operator should have when teleoperating the robot. So this video shows the development that occurred during the year. So we first applied the pipeline to the PR2 robot and was able to successfully turn a valve. We then moved on to a full-scale humanoid, the DRC U-boat, which I presented in the previous slide. Here we see the initial developments of the GUI. Then we moved on to the to a series of tests over the internet between the WPI campus and the Drexel campus, separated by 280 miles. And this is the final state of our graphical user interface that's largely based on RViz. The planner is based on OpenRave, and you can see the planner output on the left side. And we have a live camera feed that enables the user to monitor the robot's execution for errors. So we finally went to the DRC trials in December 2013 in Homestead, Florida. And we're going to dive inside our trailer during the valve turning run. And so what you can see is a captain managing the team of operators. We are successfully able to turn the lever valve. However, we're not able to turn the two subsequent valves. We believe this is due to a mismatch between the world and the model that the robot accounted for. So if you have further questions, you can come see us at the the interactive sessions afterwards. Thank you.
Okay, so I'm live. So my name is Ryan Williams. I'm the assistant here at Sparta. And I would like to invite you to talk about our later wireless optimization tool. So at a high level, RSJ combines a mobile set of agents that dynamically reconfigures to serve a set of dynamically changing information flows in a static sensor network. So the flows may change dynamically in terms of communication needs, routing needs, or they may activate or deactivate over time. But more importantly, we require connectivity not only over all sensors, but over from flow to flow. So a source to destination pairs must each be connected, and the entire mobile flow system also must be connected at all times. We apply a hybrid architecture for coordinating robots that combines the information control plane that makes the routing for communication decisions and assigns robots to flows. And we have a low-level physical control that actually implements routing, distributed routing behaviors that locally optimizes the communication per flow. So the key methodologies that we apply are follows. We implement an ETX communication model that gives us the utility per flow. And then we look at these system-wide utilities and some of the flow utilities. We make our robot flow allocations in a fairly greedy manner. We look at the detachment and release call from release call to the flow. And we attach to the most useful flow in the system while preserving connectivity. We study connectivity by looking at a multi-flow supergraph. So we can study per flow safe detachments by looking at local minimum standard trees. And then we can look at the supergraph information flow and determine which nodes serve as bridges between flows and make safe reallocations of robots between flows and in between flows. And finally, just to reiterate, we implement swarm behaviors per flow that optimize communication or routing dynamically. And just to give a little bit of a gist of what we get here, we have an initial system with active flows. We make an allocation of the robots per flow and a local swarm behavior that optimizes the flow communication. We get an activated flow that then dictates reconfiguration, and the swarm again re-optimizes the flow communication. And finally, we have a deactivation, another reallocation, and a local distributed swarm mobility implements an optimization of communication very close to each flow. So I'd like to again invite you to come see me during the interactive session. I'm Ryan Williams, and thank you for your time.
Good morning, everyone. I'm Lorenzo Sabattini from University of Modena, Reggio Emilia, Italy, and I will describe you our control strategy for cooperative dynamic behavior in multi-robot systems. So let me start with a small video. So it seems that we as a community are becoming kind of good in obtaining this kind of behaviors in multi-robot systems, so converging to a point or creating a formation or this kind of problems. But when we think about desirable applications of multi-robot system, we think more of things like this or maybe things like that. So, well, this is kind of the motivation for my work. So just to make it a little bit more formal, so essentially we have a lot of works on formation control, rendezvous, swarming, synchronization, coverage. We can see all these problems as regulation problems. So like we have the state of a multi-robot system and you want to regulate it to obtain, to make this system converge to some desired configuration. This work is something like a little step forward, and we are trying in particular to address a tracking problem. So the idea is that of having a system, a multi-robot system, partitioned into two subgroups. So we have a group of leaders and a group of followers, and we can use the leaders to inject a control action into the multi-robot system. So in particular, as you can see here, this is a sketch of the control scheme. So we use so this green ball here represents the leaders, and these are the followers. So the idea is that of having a periodic set point trajectory defined by means of an exosystem, and then we use the leader to inject a control action into the system by means of a controller defined with the regulator equations. And of course, we need the feedback from the multi-robot system. In particular, we build an output estimation and state observer system to let the leaders know the state of the system itself. So in particular, this work is on the state estimation, so every leader can measure a part of the output of the system, that is the state of the followers that are connected to them, and then we are assuming that there is a connected graph among the leaders. We implemented a decentralized estimation system to let the leaders estimate the complete output vector. And this estimate is then used to build a state observer that is an observer of the state of the followers, essentially. And this is some of the results that we obtained. So as you can see here, for example, we have that the leaders are these red robots here that move in such a way that the followers track some desired trajectory, and here you can see the tracking error that goes to 0. So thank you very much.
Looks like we're good. All right, good morning. My name is Chris Lawrence. I'm a PhD student at the University of Louisville. I did this research in collaboration with my advisor, Dr. Loff, and I'll be talking to you about adding transmission diversity to unmanned systems. The problem we targeted with this research is trying to extend communications for unmanned systems and also improve their throughput. And just take, for example, the robots depicted in these pictures here. Communications at times can be difficult for these robots based on their low antenna height, the high frequencies they're using, and the terrain being uneven that they must traverse. So we look to directivity to improve and to mitigate these situations. More specifically, our proposal deals with adding an additional radio that is combined with a passive reflector that allows you to perform intelligent radio switching combined with that. So the idea is to use the directional antenna when it makes sense to do so or when it's most efficient to do so. And the reason for the intelligent switching agent is because of saving current and energy. As you know, these are battery-powered operated systems, so therefore switching between idle and sleep states can lead to energy savings. We employ a fuzzy logic controller to perform the intelligent switching, and fuzzy logic is well suited because it allowed us to interject some human reasoning into when is the proper time to perform the switching. It also is somewhat tolerant to noise that you could expect in a wireless channel. And looking at what inputs to take in order to perform this intelligent decision, we know that you get the most gain in terms of over the omnidirectional radio at greater distances, or when the large-scale propagation effects are the most severe, as you see depicted in the table, an NS3 simulation on the left. The table on the right shows that you're going to incur a penalty doing the switching in terms of latency, because this radio was previously asleep. It needs to now connect to the ad hoc network, which is going to take some time to do that. So taking those facts into consideration, we built our fuzzy inputs of being distance and transfer size. And using some heuristics, we were able to build these fuzzy sets as shown. And the rule base that you see on the right basically states that it's best to switch to the directional antenna when the distance is the greatest and also with increasing transfer size. And we simulated our controller in S3 as well, and we incorporated the latency that I previously mentioned. And it turns out that you can still get a factor of improvement in throughput despite this latency. And that factor of improvement increases with data size and distance. I'd love to talk to you some more about this particular research and the way forward that we're looking at. We've made some modifications since employing this on physical systems, so I'd love to talk to you some more about that. Thank you.
Good morning. I am Fabrizio Nenci from the University of Bonn, and I'm here to introduce to you the research I conducted together with Luciano Spinello and Cyril Staknis. The title of this research is Effective Compression of Range Data Streams for Remote Robot Operations using H.264. We here address the problem of streaming depth range data in these situations in which the bandwidth is a scarce resource and its usage has to be kept low, as can be the case of a semi-autonomous robot communicating with a base station. So 3D range sensors are nowadays widespread, and they vary in a vast family of types and costs. But what they all have in common is that we can represent their data as depth images. So we decided to exploit the modern technologies in video compression, such as the H.264 algorithm, to compress these streams. By the way, a straightforward application of such algorithms to the depth images leads to poor reconstruction results, mainly because of the low depth resolution of the reconstructed images and because of the strong impact of the artifacts in the reconstructed images. So in order to overcome these two problems, our approach takes the depth image and splits it into slices, where each slice covers a certain interval of range values. For each slice, we produce an independent video stream so that at the other end, it is possible to collect all the streams and reconstruct the original image. By tuning the compression level of the H.264 algorithm, it is possible to adjust the byte rate. This, of course, affects the quality of the reconstruction, but we have observed that modern 3D mapping systems, such as Kinfu, are able to create discrete quality maps out of really compressed data. So to summarize, we propose an approach to effectively compress range data using video codecs such as H.264, and this allows for streaming these data on low bandwidth networks. Our main effort was to reduce the impact of those issues that appear when applying the H.264 algorithm to the depth images. And the quality of the results show a good ratio between the quality of the reconstruction and the gain in bandwidth. If you are interested on the topic, I will be happy to meet you in the interactive session. Thank you.
Hi, I'm Shenwei Yu from Marvell Semiconductor. I'm going to talk to you today the work I've done with my former professor, George Lee at Purdue University, in using a joint design method to simultaneously design mobility, data routing, and video encoding strategies for improving the network lifetime of a mobile visual sensor network. Today's technology has enabled a mobile robot equipped with a video sensing and processing capability to form an adaptive network to collect video information from the physical environment. But with limited energy powered by onboard battery, the problem how to efficiently using these limited resources to prolong the network lifetime is even more critical for the visual sensor network, which is data intensive and more power demanding. For the visual sensor nodes, it needs to compress video data before wireless transmission. Efficient video compression can significantly reduce the amount of data to be transmitted, and which saves the data transmission energy. On the other hand, efficient video compression algorithms also require high computational burdens and hence large energy consumption. By introducing the video encoding power and the performance model proposed by other researchers and combining it into our formally proposed framework of maximizing network lifetime using mobility, this paper investigates the joint design of mobility, the data routing, and visual encoding at the same time to maximize the network lifetime of the mobile visual sensor network under the guarantee of visual quality. This non-convex problem was solved by convex approximation in a distributed manner. By designing these three most energy-consuming subsystems at the same time, we are able to find a better solution that extends the network lifetime. And it is also demonstrated that with the mobility of the robotic nodes, we are able to achieve much better solution than the optimal solution in a static visual sensor network. By solving this problem, we hope to have a better understanding of the role mobility can play in a data-intensive sensor network, and also learn the inside knowledge of designing a long-lasting autonomous network. And I'd love to talk to you more during the upcoming interactive session. Thanks for your time.
Okay, good morning. My name is Katsuya Mane, and today I'm going to present work with my former intern, Jared Gerner, about displaying stick figure animations with a bunch of mobile robots. So this is just one of our results where we are using 30 robots to represent the leaping motion of human jumping toward the camera. So why we want to do this? So in case if you haven't noticed, many of our characters are actually these audio animatronic figures in disguise. And so these figures are good for displaying most of the animations, but this is not suitable for all characters. For example, if the character can stretch or shrink their body, then it's not really possible with these robots. Or there are still a lot of motions that are difficult for robots to reliably perform, like running on the water. So our colleagues in Zurich came up with this idea of using small mobile robots as pixels, and they're able to represent images or simple animations using these robots. So we basically want to extend this to more complex character animations. But we have to address a couple of issues before realizing that kind of applications. So one is occlusion. For complex 3D animations, there are a lot of occlusions that happens that hides the limbs. So you have to make those limbs invisible at certain time in the motion. Another is we want to have consistent look of the character. So we don't want to have a robot that replaces another robot in the middle of a motion, because that looks just weird. So our system takes a 3D animation and converts that to a stick figure animation and represent the motion with these small robots. But what is really interesting is what happens behind the scene. So in this case, we visualize the robots that are actually invisible to the audience. But you can see that these white circles are relocating themselves to the location that the limbs becomes visible again. So in the interactive session, I want to talk about our planning algorithm, basically, which is an offline and centralized algorithm, but has different features. For example, how to process 3D animation to ensure a consistent look of the animation, how to assign asynchronous tasks to a bunch of robots, in this case up to 75 robots, and finally, how to optimize the trajectory while the robots are invisible, and avoid collisions with other robots and minimize the velocity to realize a more accurate representation of the animation. So thank you for your attention, and see you at the interactive session.
Hi, I'm Matt Elwin, and today I'm going to talk to you about the effect of the network on performance in robot swarms. So imagine that we have a large group of robots and we want them to achieve some sort of collective behavior. There's no leader or centralized computer, so we need them to accomplish this task by communicating with each other in a communication network. So let's say we have these green robots on the left and we want them to capture this red robot in the middle. Here, there's lots of connections between the robots. This allows information to diffuse through the network quickly, and the robots can accomplish their task. If, on the other hand, we have a much sparser communication network, it's going to take longer for information to diffuse throughout the network, and when the robots try to capture this red robot in the middle, they might fail. So the point that I'm making is that the network structure influences the performance in these distributed, decentralized robot systems. Now, this is a problem because the structure of the network is often unknown prior to deployment. For instance, if we leave a bunch of robots in a field like this, they might have a nice regular communication network. But let's say 2 agents fail. All of a sudden, there's big holes in the network. Or if there's obstacles in the environment, we might get another different network structure. So what we do to solve this problem is introduce a separation principle. This separation principle allows us to treat a set of possible networks that we might encounter as a single scalar value. We don't know what the scalar value is, but we do know bounds on the scalar value. And using this, we can get the behavior of the system. So we apply, the separation principle applies to average consensus estimation. Now, average consensus estimators allow the agents to calculate global averages using local communication. And they've been used in target tracking, like I showed you, and also many other applications of interest. So if we can calculate averages, we can do a lot of things. We're going to design these average consensus estimators using the separation principle I just mentioned. And the idea is to maximize their performance over the worst network. This gives us a performance bound, so we know that no matter what the network is, we're always going to at least meet a minimal level of performance. And we do this using generic global optimization methods. So here are some results. So if we optimize the estimator for this specific network, we get pretty good performance. But if we run that same estimator on this other network, the sparse network, we get really bad performance. Now, if we use our robust design using the separation principle, we get consistent estimator performance across these 2 networks. And we can actually do this for a much larger set of networks. So each of these dots is a different network here, and we get consistent performance across the range of networks. Thanks for listening, and hope to see you at the session.
My name is Gijs Dubbelman, and I will pitch our research on robust sensor cloud localization from range-only measurements. This is joint work of Eindhoven Technical University and the INCAS Free Research Institute. The problem that we are looking at is 3D mapping of deep underground structures, like oil wells and pipe infrastructure. Typically, these environments are filled with a liquid, like oil or water. The thing with these environments is that they are globally very big and complex, but locally they can also be very narrow. Therefore, your typically sized robot will not be able to effectively explore these environments. The concept that we are currently exploring is to use massive clouds of miniaturized sensor platforms, and we want to fill the entire environment with these sensor platforms. Then, if we can reconstruct the 3D shape of the sensor cloud, we can also reconstruct the 3D shape of the environment. For this, localization is required. Unfortunately, we cannot rely on GPS, beacons, or any other type of external localization methods. The thing that we are looking at is very small sensor platforms in the size of maximum 1 centimeter. Therefore, the communication sensing capabilities will be extremely limited. We assume that the best we can do is perform ultrasound, range-only measurements between the sensor platform and a limiting set of its surrounding sensor platforms. For this, we have developed a post-graph localization and mapping algorithm that starts by constructing a seed and then uses a ransack algorithm to place new sensor platforms in the seed. After a number of sensor platforms have been added, we do post-graph optimization to reduce the globally accumulated error. So a typical reconstruction looks like this. On the left, we see the ground truth, and on the right, we see the reconstruction algorithm working. When a ransack adds a sensor platform to the sensor cloud, it is turned red. And after post-graph optimization, it's turned black. It's good to mention that we can only obtain the reconstruction up to a global rotation, but also up to a global reflection ambiguity. During the interactive session, I would like to tell you more about the working of the algorithm and also about the extensive robustness analysis that we performed with realistic inlier and outlier sensor models. I will also do a live demo of various reconstructions during the interactive session. Thank you.
Good morning. I'm Tom Apker. I'm presenting on application of grazing guidance laws to autonomous information gathering. The idea is that sheep and cattle are very efficient area coverage devices. We can model their behavior using a first-order greedy food seeker in a Voronoi cell. If we write a velocity controller that takes the desired velocity given the grazing algorithm output and nudges a robot in the right direction, we come up with a stable controller that allows us to guide those agents to the nearest food, and then use a linear system estimator to determine how well the food is eaten by its sensors. The real key challenge of this work is finding a way to convert the data we were generating to information and then treating that as food for the system. If we use just raw images, we are only going to be able to run maybe 3 or 4 vehicles at a time, even with the Wi-Fi network. If we want to use a network that can work over a larger range, like a Zigbee network, we want to go with some kind of compression that takes chunks of these images and comes up with classifiers. Then what we do is model the food in the field using a Kalman filter on each cell and throw where the covariance in the cell is the amount of food remaining, and then use the estimate to determine whether or not there is the target of interest. In this case, we're looking at finding a road map following a disaster. The result is that we come up with a pretty stable and robust method for mapping a road area with heterogeneous robots. And if you have any questions, I look forward to hearing from you with the session after this. Thank you.
Hello everybody, my name is Alessandro Giusti. I am presenting this work, which has been mainly carried out by Javad Nagy, about human-swarm interaction using spatial gestures. We are at the Dalle Molle Institute for Artificial Intelligence in Lugano, Switzerland. So our goal is to control robots within a swarm by using intuitive hand gestures, which do not require the user to be specifically instrumented apart for a pair of colored gloves. Commands are sentences formed by groups of static gestures, words. Robots classify gestures in real time and immediately provide visual and audio feedback, which greatly enhances the user experience while the sentence is formed. One key challenge when working with multiple robots is to determine who the commands are directed to. We propose a set of gestures for addressing a single robot by pointing at it, or a compact group of multiple robots within a cone, or a group of separated robots by pointing at each of them, or even the whole swarm at once. So in this example, we select the 2 robots on the left and excluded the robot on the right from the following command. This robot remains under control of the previous subject. The system is implemented by having all robots observe the subject. Each robot is equipped with a classifier for gesture classification, and the resulting classifications are shared within the swarm using an efficient consensus approach we previously published. The swarm converges to a single decision and therefore acts as a single augmented sensor. This shows an example of robot addressing. A robot determines whether the user is pointing at him or not by means of a binary classifier on the shape of the hand. Because the swarm acts as a single augmented sensor, larger swarms improve recognition rates, since more classification data is available. However, larger swarms also reduce the spacing among robots, which hinders selection accuracy. We also test that when robots are close to each other, it's harder to directly address one of them with this approach. And thank you for your attention.
Hello everyone, my name is Ali Reza Diafsoon, a PhD student at North Carolina State University. I'm going to talk about mapping on unknown environments using minimal sensor information from a stochastic SORM. This is a work in collaboration with undergrad students Joseph Batazer, Jeff Shornick, Daniel Benavides, and our advisor, Dr. Edgar Lobaton. So the motivation behind this work is the application of exploration mapping in unknown environments using a swarm of robotic agents for search and rescue in disaster scenarios, where we usually deal with unstructured and rough terrains, which provide weak odometry information. We also assume that we have GPS-denied environments with no visual sensing, where the traditional SLAM approaches may fail. So our approach to mapping is only based on local interactions, and to do so we require a topological feature extraction approach to mapping, which is based on these local interactions. So the agents perform stochastic exploration in the environment based on a motion model inspired by the cockroaches, which includes random walk and wall following behaviors. The agents can record the IDs of the nearby agents as well as the time of their encounters, and we try to construct a metric based on these local interactions. Then we perform a feature extraction approach based on topological data analysis, which is a new field of study in machine learning, which deals with extracting low-dimensional features in high-dimensional data sets. And we also propose a robust classification method for feature extraction based on the kernel density estimation, which is robust to noise and outliers. And also, finally, for visualization purposes, we represent a point cloud representation of the environments as well as a topological schema of the environments, and also persistent diagrams, which are compact representations of low-dimensional structures in high-dimensional data sets. To evaluate our algorithms, we perform both simulations and also experiments on our swarm robotic platform, which we designed from scratch for research and education purposes, which are called wolfbots. So here we can see some experiment results. We carried out some experiments to perform topological mapping using this swarm robotic platforms to be able to robustly classify between different environments, out of which 3 of them you can see in this video. And our future work will focus on extraction of more geometric information as well as extension to 3D environments, also implementation on remotely controlled robotic agents, cockroaches, and also extension to dynamic exploration of more complex environments. Thank you for your attention. I'm looking forward to see you in the interactive sessions if you have any questions.
Good morning, everyone. My name is Dan Morgan, and I'm here to present the work that we did at the University of Illinois in collaboration with NASA's Jet Propulsion Lab on probabilistic guidance of distributed systems using sequential convex programming. So the motivation behind this work is distributed systems can be used for a variety of applications, and one of the reasons for this is they have excellent versatility due to the ability to reconfigure the agents. However, this motivates the need for fuel-efficient and safe guidance and control algorithms for this reconfiguration. So the goals behind our algorithms are to achieve a desired swarm shape, minimize the fuel usage, avoid collisions, and do this using decentralized communication and computation. So the first step is to develop a high-level guidance mapping, and we do this using probabilistic guidance. We control the density distribution of index-free agents using Markov chains, where the Markov matrix represents the probability of any given agent going to a certain bin given the bin that it's in. And in both the video and the figure here, the swarm starts in a random distribution and achieves an I. So the next step is to develop the low-level trajectory generation and collision avoidance algorithm. We do this by starting with a nonlinear control, constrained nonlinear control problem, converting that to a convex problem where we want to minimize the control usage subject to dynamics constraints, collision avoidance constraints, as well as actuator constraints and initial and terminal conditions. Then we use sequential convex programming to iteratively solve the nonlinear control problem by convexifying about a previous iteration, then solving that convex program, and then repeating those steps until the solution converges. Then we use model predictive control to update these optimal trajectories in real time. So each agent will follow the optimal trajectory until a new one is calculated, and this process is repeated until we reach our terminal position. So some advantages of model predictive control is it allows us to use local communication only, gives us some robustness to external disturbances and uncertainties in our actuation, and also slightly improves the computation time. So finally, this is a simulation of 200 agents using both the probabilistic guidance and the lower level trajectory generation. So on the left side, you see the densities of each bin. And on the right-hand side, you can see the actual trajectories that the individual agents use. And as you can see, they avoid collisions when going through other bins, and they achieve the desired I shape. Thank you for listening, and I look forward to talking to you more in detail about this in the interactive session.
Good morning. I'm Sun-Kyu Lee from Rice University. Today I will talk about an application of triangulation with geodetic topological Brunel tessellations. So this is our previous work about how to construct a new triangulation. So each robot incrementally construct a new triangle and store the information called the physical data structure. The physical data structure is actually can be used to do graph mapping and can guide any robot out from its initial to final triangle using dual graph navigation. So in this paper, we are researching about the simplest application called the LRV. So each triangle first stores the metric for petrol, and the petrol robot P always move to the optimal metric neighbor triangle. In addition, we also researched about the topological Brunel tessellations, so using the geodetic half distance. So note that each robot R1 and R2 are petrol robot, and the triangle is the triangle that contains these petrol robot is the center of each Brunel tessellations. Using this Brunel tessellation, we simulated and compared the performance, and it turns out that all triangles can be covered much faster if we're using the patterning algorithm with the Brunel tessellation algorithm. So as another application, we also studied about the topological center computations. So the purpose of this algorithm is to guide a robot to the place where all robot's placement and the positions has the minimum, maximum response time by response time. So we also use the local controller like local patterning algorithm, but sometimes it converges to the local minima, not on global minimum. To solve this algorithm, we propose on message-based virtual agent. So all triangles in the same Brunel cell first generate some number of virtual agents and simulate by using the message passing and checks which virtual agent converges which triangle. By doing so, actual robot always chasing the virtual agent that has minimum maximum response time and converge to some global minima with some probability P. Thank you.
Hello, my name is Gábor Vásárhelyi. I'm from the Eötvös University from Tamás Vicsek's lab, and today I would like to present to you the Eastern European state-of-the-art of aerial outdoor swarming. So I'm from a department of biological physics where we have a long-standing understanding of animal collective motion. We make a lot of models about animals and we try to utilize that in aerial swarms of quadrupeders. So the main features of our system is that it's bio-inspired, it's fully autonomous and decentralized except for onboard GPS receivers we use. We have local inter-agent communication, broadcast type communication which is scalable to very large flocks as well. Our system is noise and delay tolerant, so it's a vacuum-free system, it's realistic and outdoor. And we can control our flock as a meta unit to make all the tasks in a self-organized manner. So we developed a hardware board with open source components like Gumsticks computer and an XP module, and integrated it into a microcopter open source quadcopter. And those who like equations, I'm ready to explain more at the interactive session. Let's see what we have achieved. We have a realistic simulation framework with all the noise and delay and everything included, where we can test all kinds of flocking algorithms, what we can later use on the robots. And this is already a visualization of real data from a very simple self-propelled particle model that is a basic model of animal motion. They look like fish in a bowl. This is a follow me function for a swarm of quadrupeders that follow a car here, and it can be treated as a two-level hierarchy for leaders and followers when the flocking algorithm ensures that the whole flock inherently maintains the connectivity metrics just by the simple rules. So we have several simple models for formation control based on the same basic rules, and one of this is simulation, the other one is real data. I won't tell you which one is which. And we also have an artistic project when we integrate human motion smoothly with the self-organized motion of drones. And that is basically it. Thank you very much for your attention, and see you at the interactive session.
Good morning. My name is Ted McDonald, and I'm Principal Embedded Controls Engineer at Symbotic. I'm going to give a brief overview of how Symbotic applies a network of mobile robots to the challenges of warehousing and distribution centers. Three key measurements of warehouse performance are case throughput rate, storage density, and cost per case. Varies by industry, but today a lot of warehouses use pallet storage and humans driving forklifts, and there's a lot of limitations on throughput, density, and cost. Enter automation. There's been a lot of interest in this field lately, and there's some great products out there. Most store products using bins or mobile shelves. This doesn't necessarily maximize storage density, so we store product directly on the shelf using a 3D storage structure to use the entire volume of a given warehouse. And we're constantly improving to increase our density. Typically in our system, we have pallets of uniform product coming in. We have a serial robot that delayers the pallet, and we singulate the cases onto a conveyor. The cases then enter these vertical conveyors where they're handed off to mobile robots operating on different vertical storage levels. You can really only see the top level in this video, but there's actually 18 levels of robots and storage stacked on top of each other in this system. The robots are coordinated via a hierarchy of centralized controllers, and these controllers are constantly solving optimization problems for task assignment, routing, and selecting storage and retrieval locations. The robots navigate in open space to travel between the vertical conveyors and the storage aisles. And in the aisles, the robots are constrained by rails and perform a relatively simple manipulation task, but we have to do this with many different case types. We scale the number of mobile robots dependent on throughput requirements, but a typical system will have several hundred such robots. When the cases are output from the system, we build a custom pallet of mixed cases that we plan in advance and have to solve a stacking problem for how to build a dense, tall, and stable pallet. And the cases have to come out in an exact sequence to execute that plan. So Symbotic now has systems either operational or in construction in 4 different market segments, and we're gaining traction in a variety of applications. We've intentionally stayed under the radar until now, and if you visit our website, you're not going to find a ton of information there, but now we're starting to kind of come out into the open. And this isn't to try and attract new customers, but to find more roboticists to come and join us. I didn't have a lot of time to go into any technical detail, but we're working on challenging problems in all different fields of robotics. So if you want to learn more, please stop by our booth in the exhibit hall. Thank you.